So as I mentioned prior to my rant, we are going to be talking about cascode amplifiers today. We will start with the derivation of the BJT cascode properties. Go through this fairly rigorously, and then we will move along to MOSFET, where we will barely look at anything because it's so similar to the BJT case. Okay. So our BJT cascode amplifier looks like this. And we are going to start with an idealized case where we are biasing our amplifier with an ideal current source. I'm going to call I ideal. And then down here below the current source, we have our amplifier. So because it's a cascode amplifier, we do have this stacked transistor configuration. Our input voltage is applied at the base of transistor Q1. And then stacked on top of transistor Q1, we have what can either be thought of as a current source, which is perfectly reasonable, or we can consider this top transistor to be a common base stage. So let me explain what I mean by that real quick. If we put a box around this guy, where we are considering this node to be the output stage of transistor Q1 as an amplifier, if we ignore everything above the red box, what is this? Common emitter amplifier. Absolutely right. So we have a common emitter amplifier. Well, if the output of the common emitter stage serves as the input to the second stage, what kind of amplifier is the second stage? Exactly right. So one way to think about our cascode amplifier is simply, it's a common emitter stage feeding into a common base stage. Now, we don't have isolation between these two stages, so our voltage gain, unfortunately, isn't simply the voltage gain for our common emitter stage multiplied by the voltage gain for our common base stage, right? There's some interrelationships that we need to pay attention to here because we don't have isolation between the two stages, and that's what we're going to talk about today. I'm going to take a moment and draw our small signal model for this guy because we're going to use it. Logan, what's up?
So is this going to be similar to when we were doing op amps and we just kind of drew a dashed line and said like this entire op amp here will give you an output voltage of blank and that will become your new input voltage?
Unfortunately, no. So the reason why I'm making that distinction is because you could assume that we can break this up into two stages and this is just the output of one changed into the input of the other. But the problem here is that this amplifier is loaded by this stage, but this amplifier is loaded by this stage. So there's not isolation between the two stages. And so we can't split it up into discrete little parts and say, well, this is going to behave like this is going to behave like this, multiply them together and call it a day. It doesn't particularly work that way at this level. There's going to be a point to where we can do that utilizing feedback and things like that, but we ain't there yet. So we have to do a more generic analysis here. Yeah. All right, so where did I put my stylus down? All right, so our small signal model for this guy is going to be a bit ghastly because it's got two transistors in it. So I'm going to start here. So this is our input signal feeding into the base of transistor Q1. I guess I should label this guy Q2. Here we have our resistance R pi 1. And so this is voltage VBE1. Here is emitter 1, and the emitter of Q1 is at ground. Here we have GM1, VBE1. Here is R01, where we are unfortunately going to be including early effects, which makes the math slightly harder. But if we don't include early effects, we can't actually see what's going on here because we're not loading these things with anything real. All right, so that's what transistor 1 looks like. So let's go ahead and add in transistor Q2. So here we'll have GM2, VBE2. A resistor R02. This is the collector terminal of transistor Q2. Here is my output terminal. This guy down here serves as the emitter of Q2. And then here I have R pi 2, VBE2, and E2. So are we okay with this small signal model? Where'd our ideal current source go? Small signal model for an ideal current source or a current source that is turned off would be an open circuit. This is why it don't show up, right? It's just the open circuit connected from here with respect to ground. It's an open circuit. It does not need to show up in our model. Okay. All right. So we're going to give this the full 335 treatment in as much as we're going to determine R in, R out, and our voltage gain. Determining R in. I am going to copy our small signal model. You do not need to do this. You do not need to redraw this in any way, shape, or form. I'm just doing it for the sake of argument here. If I could draw a box of the correct size, we can effectively do this part by inspection fairly easily. Crap, hold on. We go back up there. Copy. Paste. And we'll put it here. Okay. So if I'm determining my input resistance, all I'm really doing is figuring out the ratio between this quantity Vn and this current In, which we should be able to do by inspection for this graph. So actually, what's it going to be? R pi 1, that's it. That's all it is. Now we shall determine R out. Again, don't redraw this. We'll be drawing something, but we'll do it together. Now, in truth, we talked about what the output resistance for this stage was in class on today's Wednesday, it was Monday. Where I just said, oh, it's this value, and then we moved along happily, but I don't know that we actually solved for it in 335. So just to cover my butt, we're going to actually solve for it. Okay. So one thing that I want to point out when we're determining our output resistance, we short out our input voltage. And so this does look particularly nasty. I want to observe a couple of things here, okay? Formally, we would apply a test voltage source. I'm going to call it V out, and we would figure out what this current I out is. But before we get around to doing that, I'll just dash line right here because this dash line represents crap that's hard to figure out what's going on and crap that's easy to figure out what's going on. Okay. So let's work on the what's easy to figure out what's going on portion first. What's VBE1? 0. So what is the resistance seen looking down to everything below the dashed red line? R naught 1. Everything below the dashed red line looks like a resistance R naught 1 connected between this node and ground. Are we all okay with that? That is the same as having a resistance R naught 1 in parallel with this resistor R pi 2. It's literally between this node, which I've labeled E2, and ground, right? So from that, we can see that VBE2, looks like I'm running out of room here, but we'll try to make it happen. So VBE2 is just the voltage drop over R pi 2 in parallel with R naught 1. So I'm just going to have R pi 2 in parallel with R naught 1 here. And now we need to figure out the current, right? Because Ohm's law tells us that voltage is current times resistance. We got the resistance part online. So my argument here is that this current I out flows into this node, splits up, recombines, and then flows through the parallel combination of R pi 2 and R naught 1. So using Ohm's law, this should simply be negative I out times this resistance value, because that current I out is flowing into the negative polarity terminal. Are we okay with that? Okay. So what we're going to do now is write a KVL equation. Okay. V out is equal to the voltage drop over R naught 2 plus the voltage drop over R pi 2 in parallel with R naught 1. So that's going to be a resistor R naught 2 multiplied by I out minus GM2 VBE2 minus VBE2 based on the polarities that we've assumed. Are we all okay with that? So this voltage is the voltage drop over R naught 2, which has a current of I out minus that flowing through it, minus this voltage that we get from ground to ground. Yeah. Now I'm going to substitute in my relationship for VBE2. And so this is going to look like V out is equal to R naught 2 times I out plus I out GM2 R pi 2 in parallel with R naught 1 plus I out times R pi 2 in parallel with R naught 1. Directly substituted this relationship for VB into my previous equation. And now my output resistance, I'm going to give myself a little more space over here, is simply V out over I out, which looks like 1 plus GM2 times R pi 2, excuse me, in parallel with R naught 1. That whole thing multiplied by R naught 2 plus R pi 2 in parallel with R naught 1, which is exactly what I told you in class on Monday with no proof. So just to cover my ass, I proved it. All right, how do you guys feel about that? Anything wild or particularly crazy? Jacob. I out is flowing into the, so this I out flows into this node C2, splits up, recombines, and from here, all it sees is this R pi 2 in parallel with everything that's down here, which is simply R naught 1. So it flows through the parallel combination of R pi 2 in parallel with R naught 1. This is what I've mathematically given there. Because the current I out is flowing into the negative polarity terminal, is why I have to include that negative sign. All right, so hopefully we're feeling pretty good about R in and R out. And because we have found R out, we're going to use the short circuit transconductance to calculate our gain so that we can multiply just the short circuit transconductance times R out to get our voltage gain. All right, so not at all. Good, Logan? All righty. So we're moving along to determining our voltage gain. Again, I'm going to ask you to not redraw the thing that I'm copying and pasting. We're going to talk about it and then redraw from there. Determining. So if we are trying to determine our short circuit transconductance, all we are doing is literally shorting out our output node, determining this current, I out, and our short circuit transconductance is given by capital GM is equal to I out divided by Vn. So I want to talk about what this short circuit does before we redraw things here. It looks like you guys are redrawing stuff. It's okay. All right, so with my collector C2 node grounded, this resistance R02 looks like it's in parallel with R01, okay? I can say that because R01 is between emitter 2 and ground. R02 is now between emitter 2 and ground, but I'll be damned if R pi 2 isn't also between emitter 2 and ground. So R pi 2, R02, and R01 are all connected together in parallel. So I'm going to redraw this guy. As follows. So here is GM2 VBE2. Here is GM1 VBE1. Here's my resistance R pi 1, over which a voltage of VBE1 occurs. Here's my input voltage Vn. Here's my ground node, and I'm going to explicitly state here, this ground node is effectively the node at which E1 is, B2 is, and C2 is. Here I have my resistance R01 in parallel with R02 in parallel with R pi 2, where this node is the collector for transistor Q1 and the emitter for transistor Q2. And this is my current I out that I'm looking for. So let's start with the easiest question. Is this the same as what I had previously done? The only thing that I'm missing here is the quantity VBE2, right? Where if here's B2 and here's E2, VBE2 could be positive polarity on bottom, negative polarity on top. So now these things should be effectively the same. All right, so time for math, unfortunately. If we apply Kirchhoff's current law at our node C1, E2, we can see that I out, which is simply GM2 VBE2, is GM1 VBE1 minus VBE2 divided by R01 in parallel with R02 in parallel with R52. So it's this current plus this current. It all KCL. Circuits 1 kicks ass. All right, so a couple of things that we could recognize here. What's the relationship between Vn and VBE1? They are equal and equal. So we can replace VBE1 here directly with VN with no loss of information. So that's going to give me I out is equal to GM1 VN minus stuff. All right, we'll get to the stuff in a moment. VBE2 is simply I out divided by GM2. Right? So if this current I out is GM2 times VBE2, simple algebraic manipulation tells us that VBE2 is just I out over GM2. So that's going to give us an I out up here in the numerator, and then GM2 multiplied by R01 in parallel with R02 in parallel with R pi 2. Now it's just algebra. We move both I out terms to the left-hand side, which is going to give us I out times 1 plus 1 over GM2 R01 in parallel with R02 in parallel with R pi 2 is equal to GM1 times VN. And then from this, capital GM, which is simply I out over VN, is GM1 multiplied by GM2 times R01 in parallel with R02 in parallel with R pi 2, all divided by 1 plus GM2 multiplied by R01 in parallel with R02 in parallel with R pi 2. So this is our short circuit transconductance, but this is ugly. So we are going to make an assumption. Okay. If we are building a integrated circuit, all of our BJTs have to have the same early voltage. Literally cannot happen any other way on an integrated circuit. And we know that from our original diagram, let's go here, the amount of collector current flowing through Q2 is going to be pretty close to the amount of collector current flowing through Q1 because their betas are going to be the same. Under that constraint, this simplifies to GM1. If we were building a discrete cascode amplifier, we would have to use this relationship because these parameters would not be the same between the two transistors. Okay.
I'm a little confused now.
So what I've done here, because you're saying you should expect it to split. I absolutely understand that entirely. I'm trying to make our life slightly so what Annabelle is suggesting here, and I'm not in any way, shape, or form saying that she is remotely incorrect, is that from this depiction, it looks like I out to splits. Some portion of it flows through GM2, another GM2 VBE. The rest of it flows through R02. That combines together, and then some of it flows through that resistor R pi 2 to ground. Some of it flows through this resistance R01 to ground. Some of it flows through this guy right here, GM1 VBE. 100% agree. My argument there is simply because this resistor R02 is between this node emitter 2 and ground, we can lump it in here with this resistance as a parallel combination, and the splitting and recombining takes care of itself. I know that that might be a hard pill to swallow, and I'm not sure that I disagree with you, but it's the way that makes the math easiest, which is the way I'm going to do it. So there is an alternative derivation in one of the older textbooks that I have that effectively treats this as R pi 2 in parallel with R01, that in a series combination with R02, but that doesn't make any sense to me whatsoever. So I to some extent agree with and understand your skepticism. I'm not comfortable looking at it the other way because it doesn't make any damn sense. So we may have to agree to disagree. All right. So if you want to see whether or not this simplifies to GM1, which our end result is, and that's the exact same result that every textbook I've ever seen comes to, by all means, we can throw in some numbers and make that happen. All right, so for a integrated circuit based passcode BJT, we are going to treat our short circuit transconductance as effectively just GM1, the transconductance of the amplifier stage of our cascade. It is just, it happens to work out that way. It's not going to be that case for everything that we're going to look at in this class. This time, things worked out fairly easily for us. From this, our voltage gain, AV, is negative GM times R out, as we discussed in our previous, like last class. And so what we have here is then approximately negative GM1 times 1 plus GM2 R01 in parallel with R pi 2 multiplied by R02 plus R01 in parallel with R pi 2. When GM1 and GM2 are roughly equal, that makes R pi 1 and R pi 2 roughly equal. And if we have the same early voltages, that means R01 and R02 are the same thing. We can greatly reduce this down to GM squared times R0 times R0 in parallel with R pi, which means we have increased the gain of our common emitter stage by a factor of GM times R0 in parallel with R pi. So we get a larger gain, which is exactly what we should expect using a cascode configuration, because it inherently has a larger output resistance. All right, so let's quantify this stuff using numbers. All right. Yes, sir. Go back.
No. What did you say, like, the name of that was? You said this was
Yeah, so specifically, if we were manufacturing these transistors together on literally the same silicon substrate, right? Under that constraint, there's only one early voltage that's going to occur for all of the transistors on that substrate because we only have control over a single doping concentration level to make that happen. Okay. So all of the early voltages will have to be the same, which makes all of the R naught ones, twos, etc. They all have to literally be the same thing. We are making an assumption there that the amount of collector current that's flowing through Q1 is roughly equals the amount of collector current that's flowing through Q2, which means that our transconductances GM1 and GM2 are the same or very close, and beta 1 and beta 2 are also the same. So we're making a hell of a lot of assumptions there to get to that result. The short circuit transconductance is just GM1. That will be true or close enough to true for our intents and purposes for an integrated circuit design. For a discrete design where we can choose two different transistors having different properties, all those assumptions go straight out the window. We would have to use that long form of our short circuit transconductance to have any level of accuracy whatsoever. All right. So our goal here is to calculate the gain of the following two circuits. Or IC is equal to 1 milliamp, beta is equal to 100, and our early voltage VA is equal to 5 volts. And our two circuits of interest are a simple common emitter amplifier biased with a 1 milliamp ideal current source, where here's VN and here's V out. Let's call this guy transistor Q1. And our second is, I guess these should be VCCs, but it doesn't particularly matter. Just power supply voltage, and we're looking at small signal analysis. Here's a bias voltage, VB2. Here's our input voltage, VN. Here's our output resistance. Excuse me, our output voltage VN. So we just want to know the gain of these two things and compare them to each other. Right? The expectation here is that the gain of the cascode configuration should be appreciably larger, but I want to see how large. All right. So for our simple common emitter amplifier, our voltage gain AV is negative GM1 R01, which means that we need to calculate both GM1 and R01 in order to get it. From ELEN 335, the transconductance for these transistors is simply IC over VT. For a IC of 1 milliamp and a thermal voltage of 26 millivolts, this comes out to be 38.462 millisiemens. And R naught, which is VA over IC, comes out to be 5 kiloohms. If we multiply those two quantities together, we get a gain of negative 192.308 volts per volt. So that's for the common emitter stage by itself. For our cascode stage, where our voltage gain is given by negative GM squared times R naught times R naught in parallel with R pi, where R pi is simply beta over GM, or 2.6 kiloohms, we wind up getting negative 12,651.822 volts per volt, or roughly 66 times larger voltage gains. That's a pretty damn significant increase in the gain by cascoding here. And again, if we had tried to do this with a discrete amplifier, we would actually see that that would go down by a fairly significant amount because of all those mismatches and assumptions. All right, so the next topic we're going to talk about literally shouldn't take more than a couple of minutes is we don't have access to ideal current sources. Practically, right? So a more typical passcode configuration would look something like this. We would bias our cascode amplifier. I'm going to call this VB4, this guy VB3, which means this is transistor Q4 and this is transistor Q3. I'm going to take my output voltage here. Here's Q2, here's Q1, this is VB2, this is VA. So we are biasing our cascode amplifier, which is the bottom half of the circuit, with a cascode PNP current source, which is the top half of the circuit, right? That is obviously going to change our output resistance appreciably. So we should see that our gain will go down because our biasing current source no longer has an infinite small signal impedance. So let's call this resistance R out P, and the resistance looking down, R out N, right? We know from our analysis literally just a few minutes ago that R out N was 1 plus GM1 times R naught 2 in parallel. Hold on, I think it might be R naught 1 in parallel with R pi 2. My apologies. R naught 1 in parallel with R pi 2. All of this multiplied by R naught 2 plus R naught 1 in parallel with R pi 2. We should easily be able to surmise what R out P is because it's just the same cascode configuration, except it's using PNP transistors, right? So I would argue that literally by inspection here, we're going to call this 1 plus GM3 R0 in parallel with R pi 4 times R0 4 plus R0 in parallel with R pi 4. And from this, our voltage gain is simply negative GM1 times R out N in parallel R out P. So if transistors Q3 and Q4 were identical, except for the fact that they are obviously PNP transistors and not NPN transistors, and all other parameters were the same, what should we see the voltage gain of our cascode configuration fall to? How about that? So this guy with an ideal current source effectively represents the maximum possible achievable gain. The maximum practical achievable gain is half of this, because the best thing that we could do would be to make this PNP current source exactly match the NPN state, right? If there's any mismatch whatsoever, that parallel impedance is going to be less than half of our N side, which means our gain is going to be small. Why would it be an absolutely terrible idea to bias this with a single PNP current source as opposed to a cascode current source? Pretty much, yeah. So it would be, you would have the output resistance. So it would be this extremely large output resistance in parallel with just R0, which is going to look like something a little bit smaller than R0. So it's actually going to behave slightly worse than the common emitter stage by itself. So it's a real bad idea. All right, we got 15 minutes left. That's actually more than enough time to talk about MOSFETs. So MOSFET cascodes. That was a cascoded current. I don't recall, maybe. Yeah, let's find out. So we're just going to go full on into the practical version of it. Let's call this VG4 for transistor M4, VG3 for transistor M3. This is VDD up here. Here's our output voltage, V out. Here's VG2. Here's VN. This is M2. This is M1. All right, so without doing any real analysis whatsoever here, the fundamental difference between the MOSFET version and the BJT version is that R pi is infinity now, right? Which means our input resistance is infinity ohms. Okay. Let's define this current here to be R out N. This current flowing up will be R out P. So if all of our R pi's are infinity, what that means is that R out N is 1 plus GM1 times R naught 1 multiplied by R naught 2 plus R naught 1, and R out P is 1 plus GM3 R naught 3 multiplied by R naught 2 plus, sorry, that shouldn't be R naught 2, that should be R naught 4. R naught 3. Well, as we talked about in 335, this effectively comes out to be R naught 1 plus R naught 2 plus GM R naught 1 R naught 2, which is going to be approximately just GM1 times R naught 1 times R naught 2 in most cases. By the same rationale, this guy will be GM3 R naught 3 R naught 4 approximately. It's not going to hurt anything to use the approximation the overwhelming majority of the time, but if you feel more comfortable not approximating, just use this first one and you'll be good to go. Okay. Our voltage gain, AV, is just going to be negative GM1 times R out N in parallel with R out P. Under the constraint, okay, so let me point something out here, okay? Our short circuit transconductance, GM, and I'm getting this literally from just setting R pi's to be equal to infinity, is going to come out to be GM1 multiplied by GM2 times R naught 1 in parallel with R naught 2 over 1 plus GM2 times R naught 1 in parallel with R naught 2, which is approximately equal to GM1 if 1 over GM2 is much smaller than R naught 1. Now, here's another caveat type thing, okay? So when we were talking about an integrated circuit cascode for BJTs, we were restricted to the fact that all of our different devices had the same early voltage, which means they all effectively had the same value for R naught 1, R naught 2, et cetera. All of those are equal. In an integrated circuit MOSFET, the designer has control over both the width and the length of every single MOSFET, which means we have control over the channel length modulation coefficient. So there is no guarantee whatsoever that all of our output resistances for all of our transistors will be the same. It's only true if we design them to have the same, the transistors have the same area, okay? So we can play around with things and actually change transconductances, change output resistances, all that kind of good stuff by playing with the aspect ratios and the physical size of our transistors to get whatever specific point we want. So there's a lot more flexibility by the designer in a MOSFET based configuration than there is in a BJT based configuration. So that's why I'm not going through here and lumping things together and calling this GM times R naught squared. It's not guaranteed as much as it is in an integrated BJT. All right, so this is MOSFET cascodes. Do we need to go further? Not particularly. BJT is the much harder case to understand. All right, so what I hope to talk about on Friday is cascoded current sources. Now we're tying things back around, or cascoded current mirrors. So how we bias these guys practically. So how we bias circuits with a high input resistance or high output resistance current source. Well, so we'll talk about cascode configuration, and then if we are constrained by headroom or whatever to only be able to effectively use single transistor based devices, we'll talk about the Whitlar scheme and the Wilson scheme, which also have large output impedance.